Pode começar.
Obrigada. Welcome everyone to today's seminar. It's a pleasure to introduce Elisa Ferreira, who is currently a research fellow at the Max Planck Institute for Astrophysics in Garching, Germany. Elisa received her PhD from University in Canada, and later this year will start a position as an associate professor at the Physics Institute of the University of São Paulo. Her research is mostly focused on studying the dark sector, and more specifically dark matter, focusing on ultralight dark matter. Testing those models using the current observational probes and new observational windows are also part of her research. Elisa is part of two telescope collaborations, the Prime Focus Spectrograph, the PFS, and BINGO, Baryon Acoustic Oscillations in Neutral Gas Observations. Thank you, Elisa, for accepting our invitation. You may start when you're ready.
Thank you very much, Anna. It's a pleasure to be here giving a talk to you. I wish soon we can all meet in person and I can visit you guys and give this talk in person. So today I'm going to talk about this, which is one of the leading candidates for dark matter. I prepared an overall review of this class of models, which has features that are a little bit different than other dark matter models. And so I'll introduce these models today. And in the end, I'll talk a little bit about the bounds that we have nowadays for the most famous model, the fuzzy dark matter model. So let's start. Sorry. Okay, so I don't need to convince this audience that for the evidence for the existence of dark matter. Nowadays, the evidence for dark matter comes from different systems. It's a huge amount of evidence coming from all scales, from cosmological scales to galaxies and substructure. And each of these systems not only tells us that the need for the existence of dark matter, but also a little bit of the properties that dark matter needs to have. So we can be able to, maybe in the future, discover what dark matter is. The best observations that we have nowadays come from the large scales. And these large scales, which are the most precise observations that we have nowadays, allow us to build the standard cosmological model that we have nowadays as the paradigm that we have to describe the evolution of our universe and to describe all the components that are in our universe. In this model, dark matter is described by this cold dark matter fluid, which is a hydrodynamical description or a fluid description that describes dark matter, that dark matter should behave on large scales as a cold fluid, which means that it moves really slow, pressureless, which means that it clusters on all scales, dark or transparent, as some people would say, which means that it doesn't interact with all the visible matter that we have or interact really weakly, collisionless, it doesn't have self-interactions. And also we know what should be the abundance of dark matter today. So what is the amount of dark matter today? So we know that most of the matter that we have today must be dark matter. And around 25% of our universe should be made of dark matter. So this is what we know about dark matter. And we know very precisely because those large scale observations give us a very precise measure for the lambda CDM model. So on large scales, a dark matter should be cold dark matter. However, although very successful, this paradigm, this cold dark matter paradigm, has some problems. And we don't know some things about dark matter. So the main thing that we don't know about dark matter is what is dark matter. So although we were able to measure many of the properties of dark matter and with a very impressive precision, the nature of dark matter is still a mystery for us. And we can invoke many different mechanisms to explain these precise observations that we have nowadays. So we can go from modified gravity to new particles, to composite objects. And all of them could be different descriptions, different macroscopic descriptions for dark matter, but they still behave as cold dark matter on large scales. We can see, for example, here in this mass scale that dark matter could be from a macroscopic solar mass object like a primordial black hole until an ultralight dark matter, a new particle that will be extremely light. So this can be seen, this amount of not knowing what dark matter is, can be seen in this 80 orders of magnitude of possible models for dark matter that we have, which is a huge imprecision or a huge question that we have in theory. But there's also more that we don't know. We don't know the nature of dark matter. But actually, all of those things that we said that we know about dark matter on large scales, they actually don't need to hold so precisely. So nowadays, we ask the questions like, dark matter needs to be cold in large scales, but how cold? We can have models like warm dark matter that can also explain the data that we have nowadays. We can also say that it doesn't need to cluster on all scales, or maybe we can have a very, very tiny interaction with baryons or other matter that we have in the universe. And also they can have a small self-interaction. So although we know how dark matter behaves on large scales, and it should follow the CDM, on small scales, this behavior is still weakly constrained. So we still don't know quite well how dark matter behaves on small scales. And those small scales have been revealing to us some different properties that dark matter might have. And as these observations that we have on small scales and also the simulations on these smaller nonlinear scales have improved, some of these challenges about the description of dark matter on small scales have emerged. So here we can see, for example, the cusp core problem, which is this, this incompatibility between the simulations with dark matter only that predict this NFW profile, which is a profile that gives you a cuspy core towards the center of the galaxy. So it diverges towards the center of the galaxy. This is the density per radius. And what we actually observe are cored galaxies, or at least some cored galaxies. There's also other challenges, like the missing satellites, which is this incompatibility between the number of predicted satellites in CDM simulations versus what we observe. But maybe the one that I personally like the most are related to this regularity versus diversity of rotation curves, which tells us that although galaxies are incredibly diverse, we have galaxies of different shapes and sizes and all, they're extremely regular. And this is embodied in some of these scaling relations that we have. For example, one of them, and the most famous one, is the baryonic Tully-Fisher relation, which is this remarkably tight correlation between the baryonic mass in these galaxies and the circular velocity that we can see here in this line. So the spreading of these points of each of these galaxies is smaller than the error of each point. So it really shows a very tight correlation. And this doesn't agree with what is predicted by a CDM-only simulation. Of course, although these challenges or these curiosities are very interesting, we have many possible explanations for it. And the first one is obviously feedback. So we were talking about simulations that were CDM only. We need to include baryons, and the effect of baryons can really explain all of those curiosities. And this is what those have been showing in the lately. So we have been seeing that different simulations that include baryons have been showing that they can reproduce or explain most of these problems, although it's still very difficult to explain the tightness of the scaling relations. In the past, some people told us that we could maybe explain those things by modifying the the dynamics that we have in galaxies. So for example, to explain rotation curves or these scaling relations, Milgram realized this empirical relation that I showed here, which tells us that for high accelerations in a galaxy, those are going to follow a Newtonian acceleration of the baryons. And if you are in a regime that you have low accelerations, this is going to follow the geometric mean of this Newtonian baryonic acceleration and this A naught, which is a factor that can be found from fitting these curves. So of course, nowadays we know that Mond, in the way that Milgram tried to coin on that time, which is a theory of modified gravity that doesn't need dark matter, doesn't work in the way he coined it, because it doesn't explain clusters or CMB or even any large-scale observations. But this empirical relation, which I'll call Mond from the rest of the talk, it's still a very good fit to the rotation curves of galaxies. So we'll be very, very interested to see if we can get this relation from, for example, a modification of dark matter, which is the third thing that you can have to explain this curiosity or this different behavior that dark matter can have on small scales. And this is what we're going to follow now. So we're going to follow an explanation, which is, can we modify the dark matter paradigm from the normal CDM to explain either these challenges on small scales, or even more important, since we have this we're not so constrained on small scales, what is the freedom that we have to create different dark matter models that have a different behavior on small scales that can be probed in the future with small scales observations. And this is the main idea behind these ultralight dark matter models. So these ultralight dark matter models, they were first thought as models that would explain these small scale challenges. But I think they're much more than that. So even if those small scale challenges are explained by, now we have better observations so we can explain better, or now we have better simulations so we can explain those, I think those models are still valid because they give you a very rich phenomenology on small scales that is still not probed, but that can be probed in the near future. So they're very interesting models. So what are ultralight dark matter models? So when we talk about ultralight dark matter models, we're talking about the lightest possible candidates for dark matter. Anything lighter than that will behave like dark energy. So we're talking about candidates that have a mass around between 10 to the 22 eV, which is 10 to the minus 57 kilograms, and eV, which is 10 to the minus 35 kilograms. Just remember that a WIMP, which is what was the most famous candidate of dark matter in the past, it is around GeV. So we're talking about really, really light candidates. And to be that light, we need to have bosons. Dark matter needs to be a boson, cannot be a fermion. And it needs to be non-thermally produced in the universe. So the limit for thermal relic dark matter is around QeV. So we're really talking about really, really light candidates. And what happens when I have a very light dark matter candidate? So what is interesting about dark matter that is that light is that it has a very large de Broglie wavelength. So let's remember what this means. So let's go back to physics, quantum mechanics, the wave-particle duality. So when we're talking about those experiments that we have back in the days about the double slit experiment, for example, you see that if you have electrons in this double slit experiment, they are actually going to be explained more by a pattern like a wave. Although we know that electrons can also be explained by being like a particle. So we know that particles, any particle in our universe can be explained as a wave or as a particle. And why we don't explain usually particles in our daily life as waves is because if you have a very large mass, for example, here a golf ball, your de Broglie wavelength, which is defined by 1 over the mass over times the velocity that this particle has, oh, sorry. So if I have a very heavy object, this will have a tiny, tiny de Broglie wavelength. But we can see here, for example, an electron which is very light, which is still not as light as the dark matter that we have, you'll have a bigger de Broglie wavelength. So if I have a very, very light particle, this particle will be represented by a wave with a wavelength given by the de Broglie wavelength. So for our candidates here, which goes from 10 to the minus 57 kilograms to 10 to the minus 35 kilograms, this gives us de Broglie wavelength of order of parsec to kiloparsec. So these particles, the advantage of these particles of having this ultralight candidate is that since they have a de Broglie wavelength, which is of order of kiloparsec, inside galaxies, they will behave like a wave. So they will have a de Broglie wavelength, which is of order of the size of the galaxy. So when I'm looking to a galaxy, or to all the dark matter in the galaxy, you're actually looking at the wave, the macroscopic wave of dark matter. But if I'm in distances much bigger than the galaxy, so if I'm far away and looking at the galaxy from far away, I actually see this as point particles. So from large scales, dark matter is going to behave like standard particle dark matter. So I see this dark matter as particles, normal particles. So this behaves like CDM, recovering all the successes that we know CDM has. But inside galaxies, because the de Broglie wavelength of this ultralight candidate is of order of the size of the galaxy, dark matter will behave very differently. So dark matter that has a mass in this range will be of the size of the galaxy. So inside galaxies, this candidate will behave as a wave. And this is the main thing that is going to drive this different dynamics or this different phenomenology that dark matter will have on small scales. There are many ways that we can achieve this. So we can have many different models that can describe this behavior, that can have bosons that are ultralight and describe dark matter on small scales. Although we have these many different types of models in the literature, they can actually be divided into 3 classes. So these 3 classes tell you what mass of dark matter you can have and how they would behave in galaxies. So each of these classes has a different behavior of dark matter on small scales, and they are described by a different dynamics. So the first class that we can talk about is the fuzzy dark matter, which is probably the most famous one, which are basically just a boson, which is ultralight under gravity. So it is like having a WIMP, which is just a boson or a fermion or whatever particle that you have under gravity. But in this case, this is an ultralight boson. So this model is described by only one parameter, which is the mass of this particle. You can also have the same model as fuzzy dark matter, but you include self-interaction. So this is like having self-interacting dark matter, but in this case, it's self-interacting fuzzy dark matter. So you have self-interaction between each of the dark matter particles. So they interact, dark matter interacts with dark matter, but you have still a very light candidate for dark matter. And the third candidate is called dark matter superfluid. And this is very interesting. I won't have time to talk about it, but this is a very interesting model because you can actually have a dark matter particle which behaves which inside galaxies, given this wave description, it behaves like MOND. So it reproduces that empirical relation of MOND inside galaxies. So in this way, in this model, you can actually describe using almost something very similar to MOND, all the rotation curves and all the scaling relations, while you still have CDM on large scales. I have some slides about it. I won't have time to talk too much about it. It's also the less constrained model, but it's a very interesting class of models. And it shows us, because it has a very general type of Lagrangian, so the way that you can describe it, it tells us that we can actually describe two types of phenomenon, two types of dynamics using only dark matter. So it's a very interesting model. I'll talk more today about the fuzzy and the self-interacting dark matter, which are the most famous models and the most constrained ones. They are the most famous also because the axions or axion-like particles are part of these models. I'll talk a little bit more about axions, but axions are very interesting because they are particles that have this. They are particles that they were invented in particle physics to resolve the strong CP problem. So they have this motivation from particle physics. And they must be ultralight to explain dark matter, for example. So axions are part of this too. They have the same phenomenology as these two models. And the very interesting thing is that they are described by the Schrödinger equation, as I'll show. And as I said, what happens in consequence of having this wave behavior in galaxies, because they have this W wavelength that is of the size of galaxy, is that you're going to have a very rich phenomenology on small scales. So dark matter is going to behave very differently on small scales, which will allow us to probe these models using small scale probes, but also cosmological probes. So let's talk a little bit about the fuzzy dark matter model and the self-interacting fuzzy dark matter model. So we call this fuzzy dark matter model because given that it's a wave and you have interference of waves, the way you see the galaxy in simulations now is a little bit fuzzy, like this image. So that's where this fuzzy name comes. So there's nothing special, it's just a funny name that we like. And this is this class of models that it could be any ultralight particle. I can use any ultralight particle that I just invent a phenomenological model, or it can be described by these axion and axion-like particles. So axion and axion-like particles are axions in special, what we call the QCD axion. It is a particle that comes from particle physics. It was coined to explain the strong CP problem in QCD, so we don't need to talk about that. But it has a very good motivation from particle physics, like I said. Axions are also ubiquitous in string theory, or we can also produce axions in models of inflation and axion-like particles. So axion and axion-like particles that have particles around 10 to the minus 22 eV or even lighter, they behave like dark matter, and they're going to behave the way I will describe these models. So how does these models describe dark matter? So I have just a little bit of equations here. Please let me know if this is not clear. So like I said, so I can have this really small mass dark matter. I need to explain this dark matter needs to be a boson. So the way that in field theory I explain a boson is by using a scalar field. So these models are explained by a scalar field in gravity. So in a cosmological background, like a Friedman-Hobson-Walker background. And they're given by this equation of motion, which is phi is the scalar field, h is the Hubble parameter, m is the mass of this field, and g is the self-interaction. So if I don't have this g, I have the fuzzy dark matter model. And if I have this self-interacting part with G, I have the self-interacting dark matter model. And the way that this describes dark matter is that I have this potential. So this term here describes this potential here. So my particle, as the universe evolves, is going to slow roll it down into this potential until at some point, it's going to reach the bottom and it's going to oscillate in the bottom of the potential. And this phase where it oscillates around the bottom of the potential is where it behaves like dark matter, because if you take the average of this equation of state, this is the equation of state, which is 0. So it behaves like dark matter. So the mass of this particle needs to be exactly, or more or less, it needs to be of order of the Hubble parameter at recombination, so it behaves like dark matter. So this already tells us that to be dark matter, these models need to be a very small mass, need to have a very small mass. But we're not going to talk about cosmology today, so this is only to motivate. We're going to talk about the small scales because this is where the interesting behavior of these models are. So if I take the non-relativistic limit of this equation, I get this equation for the behavior of these particles. Since we are interested in galaxies, so the non-relativistic regime, it is what we are interested. We take the non-relativistic regime of that equation. And this gives us this equation, which is exactly a Schrödinger equation. So if we go back in quantum mechanics, a Schrödinger equation is the equation that describes the evolution of the wave function. So it is really what describes the evolution of this wave that we have in quantum mechanics. Here, dark matter on galaxies then, although it behaves classically, it's going to follow a Schrödinger equation. So here in this equation, psi is what represents our scalar field, is what represents our dark matter. Phi here, this capital Phi here is the gravitational potential. So this equation is coupled to the Poisson equation. So this is the Poisson equation that describes how the gravitational potential relates to the density of my halo of dark matter. And if G is equal to 0, I have the fuzzy dark matter model. And if G is different than 0, I have the self-interacting fuzzy dark matter model. So they're both described by the same equation. You either have this term or not. So here we can already see that this model is fundamentally different than CDM, than warm dark matter and the self-interacting dark matter. This is actually described by this wave equation, this Schrödinger equation. So we expect that the phenomenology is also going to be a little bit different than what you have for warm dark matter or self-interacting dark matter. I can do a change of variables, and I like this one that is written here, where I'm going to associate this boson that describes my dark matter with a density, and also the phase with a velocity. So I can rewrite exactly this system of equations as the system of fluid-like equations, which we call the Madelung equations, where here is the conservation of the density, and here is an Euler-like equation. But this Euler-like equation is a little bit different than what we have for CDM or for any other fluid, because it has this term here, which is called quantum pressure. It is called quantum pressure because the first time that this was realized was in context of quantum mechanics, where you had a Schrödinger equation. But this is also happens if you have a classical system. And this term is not present if you have a CDM or if you have a warm dark matter or if you have a self-interacting dark matter. So this is only present if I have this wave-like dark matter. So this quantum pressure is going to counteract gravity. So we can already expect a different behavior than these models. I also can have a pressure here that comes from the interaction if I have the self-interacting dark matter. So this term here in my Euler equation, in these fluid equations, already tells us a lot about how different the phenomenology is going to be on small scales. Now I'm going to have this counter pressure, quantum pressure going against gravity. Or in the case of self-interacting dark matter, quantum pressure going against gravity and the attractive pressure, or the other way around. This tells us this competition between gravity and quantum pressure tells us that we're going to have this, this Jeans length here. So those models have a finite Jeans length, which is exactly where you have equilibrium. So inside this region, it is the region where quantum pressure wins. So I have no structure formation. And outside, it is a region where gravity wins. So I'll have clustering will proceed as normal. So in the fuzzy dark matter, we can have Jeans length, which is of the order of 55 kiloparsec if I have a dark matter that has a mass around 10 to the minus 22 eV. So we have a finite size Jeans length. So we have a finite size region where I won't have the formation of structures. So throughout the evolution of the universe, when I'm forming structures, all the structures with wavelength below this Jeans wavelength are not going to be formed. For example, if I have a mass model with a mass smaller than 10 to the minus 20 eV, this Jeans length is of order of kiloparsec. So this, for example, could solve problems like the missing satellites problem, or any matter of not having structures on small scales. If I have self-interaction, this proceeds a little bit different. For example, if I have an attractive self-interaction, this Jeans length is tiny. And if I have repulsive interaction, this Jeans length can be very different. Can be big or small. So this really shows that those models, they are going to have very different phenomenology. And now we can describe a little bit of this phenomenology. So we know that those models are described by this Mondelong equation, and they're going to have a finite Jeans length. So they're not going to have formation of structures on small scales. So what does this mean for this phenomenology? What are the possible things that these models can predict? First, let's start with the suppression of small structures. So given this finite length, Jeans length that those models have, we won't have the formation of structures on small scales. So if we calculate, for example, here we have below a CDM simulation, and here we have a fuzzy dark matter simulation. So by eye, we can already see that this fuzzy dark matter simulation has much less small structure than a CDM simulation, because this is suppressed by these models. We can also see this by calculating, for example, the 2-point correlation function, like I'm showing here, and taking the Fourier transform. So we can have the power spectrum. Here I have the power spectrum over K scales. And we can see, for example, that depending on the mass, so the smaller the mass is, the bigger the suppression that I have of the power spectrum on small scales. So if I have, for example, here a 10 to the minus 22 candidate, here, this green one, we're going to see that in comparison with CDM, which is the blue curve here, we're going to see that on small scales, we have a huge suppression of the formation of structures. This suppression of the formation of structures can also be seen in the halo mass function. So since I'll produce less halos, so I'll produce less small halos, I'll also have a different, less structures on small scales and less galaxies on small scales. So we can see all this in the halo mass function here, that, for example, for 10 to the minus 22, which is this curve, gray curve, we can see that we don't produce halos that are of the order of 10 to the 8 and smaller mass. And this is one of the motivations, for example, for these models to solve some of the small scale challenges. Another very interesting phenomenology of those models is the formation of cores, solitonic cores. So here we're talking about linear scales, but we can go to nonlinear scales, and for that we need simulations. So if we evolve those halos, here we have a simulation that I'm working on in collaboration with a student, Joette Chen. We can see that if we evolve one single halo, there is the formation of a core in the middle of the halo. So because I have this region where I don't have structure formation, I'll have the presence of this core in the middle of the halos, of the dark matter halos. So we can see that in those models, then we're going to have that the profile, the density profile of dark matter, of the dark matter halo, is going to have a core in the middle and an NFW outskirts in the outer radius of this halo. From simulations, we can describe how this core profile should evolve with respect to mass, and also how it should relate to the mass of the halo. And this is very important, this relation, how this profile and how this relates to the halo. It's very important for us to really check, to compare with observations and be able to constrain, for example, the mass of this model. So this is actually what we're going to use to compare with, for example, the profiles of dwarf galaxies, ultra-dwarf galaxies, to see if there is the presence of a core in those systems. Again, I'm with Joette Chen, the student that I'm working with. We are actually doing simulations to check the relation between the core, the mass of the core and the mass of the halo. This relation here that we have, it was made in 2014 by one group, and no one ever checked, and we are checking this and we're finding different results. So this is just a work in progress. And we're also doing the same for the self-interacting fuzzy dark matter. We also have a simulation for that. And we can show that depending on the attractive interaction or the repulsive interaction, we'll have very different structures being formed. And this is the first simulation of this kind. So those simulations are very important for us if we want to understand really how those halos are formed, and we can compare then this with the observations. Another very interesting phenomenon that we have if we have dark matter being this ultralight dark matter is wave interference. So as we could see here in the simulation, while we are forming the halo, we will have that this dark matter, because this dark matter is made of waves, we're going to have these interference patterns, these destructive and constructive interference patterns that we can see better here in this figure. Here's another simulation that shows not only the halo, but also a little bit of the cosmic web, where you also see these interference patterns created by the fact that we now have dark matter being a wave. We call these granules because this will have a size of the order of the de Broglie wavelength of the particle that we have. And although this is a very interesting phenomenon that only happens in this type of model, we believe that this is very hard to observe, and no one has ever come up with a good observational system to be able to see that. So any ideas are welcome. Another very interesting phenomenon for the fact that this is a wave, it is the formation of vortices, which are sites where the fluid velocity is vanishing. So here the fluid velocity is vanishing, but you have a non-vanishing circulation here. So this happens when I have, for example, this destructive interaction. So if I'm in a place here where I have destructive interaction, this can be the place where you have zero velocity and a vortex can form around it. So you can see, so those vortices are going to form if I have this fuzzy dark matter model. And also if I have the self-interacting fuzzy dark matter model, because if I have rotation in those models, I'll also form this, these sites where you have vanishing velocity. I won't talk too much about it because this is ongoing research. But one thing that is interesting is that if you find those vortices, this can only happen in wave-like dark matter. So this will be a smoking gun prediction for this model. The predictions that I said before, all the ones that we discussed before, they could be degenerate with, for example, warm dark matter or self-interacting dark matter. But this type of predictions are really smoking guns of those models. So these are the type of things that we are looking for now in other groups. So we have here, for example, some simulations for the fuzzy dark matter, where we can see here some vortices. So you can understand how hard it is to really describe those vortices. So I think that is the difficulty that everybody now is having in the community, is like, how do I really see those vortices? And this is in high redshift. So when you get to low redshift, where these things start to merge and all, this can be very complicated to describe those vortices. And this explains the figure that I showed first in my slide, this artistic view. So if we can actually describe those vortices, the sizes of them, and also predict their abundance, we can actually say if they're observable or not, and which probe that we can use to observe them, either celestines or strong lensing. So this is a very important signature of these models. So the third one are dynamical effects. So these models, since you have a wave in the interior of your halo, they behave very differently, and they can have various dynamical effects like relaxation, oscillations, a different dynamical friction, and also heating. For example, relaxation. This is actually the formation of a Bose-Einstein condensate of a superfluid. So what is this? So a Bose-Einstein condensate is this macroscopic phenomenon, quantum mechanical phenomenon on small scales. So what is a Bose-Einstein condensate? So a Bose-Einstein condensate is a gas that if you decrease the temperature until a critical temperature, all the particles of this gas are going to go to the ground state. And now this gas is not going to behave anymore like a gas of single particles, but it's going to behave like a collective system. So all of these particles are going to behave together. They're not going to behave as each individual particles. And this is described by having this, wave function, this macroscopic wave function describing the entire system. So the system is not anymore a system of individual particles, but it is a system described by this wave function, macroscopic wave function. Another interesting system, which is a superfluid, which is exactly a Bose-Einstein condensate when you have interactions, when you have self-interaction. And it's actually a system where after you condense, you get to this critical temperature and the things go, all the bosons go to the ground state. They actually have a different dynamics. They now flow without friction. So if you have this system, you have a fluid that doesn't have friction. And for example, here they measured this in laboratory, and you can see that when it reaches superfluid, it actually starts to go around the cup and drip. So there's no friction to hold it inside the cup. And those systems, Bose-Einstein condensate and superfluid, they're actually describing by exactly the same equation that we have described by dark matter, which is the Schrödinger equation. So there is the possibility that those ultralight models can actually condense on small scales. So I have this macroscopic quantum mechanical phenomenon happen inside galaxies. This has been shown by simulations. Here we can see a simulation without a condensate, and this is only a halo under gravities. And we can see that you form a Bose-Einstein condensate after some time. I won't talk too much about it because this is an open question if you really have the formation of a condensate or not. But this is a very interesting phenomenon that you could have really a quantum mechanical phenomenon happening on galaxies. You can also have friction or heating. I also won't talk too much about it, but this can have really important observational consequences. So let's now, in the remainder of the time, I know I don't have too much time, talk a little bit about the implications of all those predictions. We're going to see that these have implications on large scales, but mainly the strength of the constraints are going to come from the small scales. And I'm going to illustrate that using the fuzzy dark matter model because this is the most studied models of them all. And this is the one that has the best bounds. So here in this figure, I'm presenting to you the current bounds on the mass of this model, where the highlighted regions are the excluded regions. So we can see here that there's not a lot of room for this model to happen. And this comes from the many different observations. For example, we can see this one from CMB, Lyman Alpha, and 21 centimeters. These are actually probes that are going to probe the suppression of small structures. So this is going to probe the first prediction that this model has, that it suppresses the structure. So we can use CMB, for example, to put a bound on the mass. We can use 21 centimeter, the global signal. But the main constraint that we have nowadays comes from Lyman alpha, which means that if I have the suppression of the formation of structures, so I don't have the small halos, so this will impact reionization. So this will impact the galaxies that you can form on large scale, on large redshifts. So you need to have this bound on the mass, so you have enough power on megaparsec scales in the Lyman alpha forest to really explain the observations that we have. So really this suppression of small scale structure can really impact many different observables. And Lyman alpha nowadays is one of the most powerful ones. You can also probe the suppression of small scales by, for example, stellar streams and gravitational lensing. So using this gravitational probes, because they probe actually substructures. So they probe the existence of substructures. So if I have these models like fuzzy dark matter, I'll have much less small substructures than CDM, for example. So I can use, for example, the stellar stream and see if like they use GD1 here to see if the gaps that you have in this stream are compatible with the absence of small scale structures of null. And this gives us this bound here. We can also use dynamical effects like dynamical friction and heating to put bounds here. For example, you can use the Fornax globular cluster that should have merged with Fornax and didn't. This put a bounds on the mass. And also you can use the thickness of the Milky Way disk to probe if you can have heating or not, due to the fact that you have this type of models. You can also use the phenomenology of having a core to put bounds on the mass. And for that, we can use dwarf galaxies, dwarf spheroidals, or also ultralight galaxies, ultra-faint dwarfs, sorry. And ultra-faint dwarfs, which we did in this work here, are currently the strongest bound that we have in this model. Here, the strongest bound is represented by SEGI1. And what we do is that we try to fit this profile, which comes from simulations, which tells us that there is the presence of this core inside the galaxy with an NFW profile around. So if we use, in this work, we use the data, the stellar kinematic data from 18 ultra-faint dwarfs, which we can show here, to fit this, to tell us if there is the presence of a core or not in those systems. And this actually gives us a very large mass in comparison to what we expect. So this type of large mass gives you tiny, tiny cores. So although this looks like a measurement, this looks like the first time we measured the mass of fuzzy dark matter. Actually, we don't consider that a measurement because those cores are so small that we think the uncertainty is really big to claim this as a measurement. But these are the strongest bounds to date. I don't have time to talk about sporadian, sorry. So in the end, these are the bounds that we have for the fuzzy dark matter. 10 to the minus 22 here would be the special mass to explain all the small scale problems. We can see that this is completely ruled out. And actually, if the fuzzy dark matter seems to be, if it exists, if this is the model, it seems to be something around 10 to the minus 20, which is a much less interesting because it has much less effects. But still, this is a possible mass. So in the future, we hope we can constrain the other models like the self-interacting fuzzy dark matter model and also the dark matter superfluid model with the future observations, and also closing in this range of models of fuzzy dark matter, which is already, this already shows us how strong the small scales are to really probe this type of models, which is, in my view, very interesting. But in the future, with instruments like PFS, and also, for example, BINGO, the 21 centimeter radio telescope, LSST, of course, and the CMBS-4, we really can make this much better. I won't have time to say, I just want to do a little bit of propaganda of PFS. PFS is really an exquisite instrument to measure dark matter. So PFS is a spectrographer that we are going to put in the Subaru telescope. And it's going to have three different science goals: galactic, cosmology, and galaxy evolution. And all of those are going to measure different parts of dark matter. So all of those three science goals are going to measure one of those different observations. So PFS alone can actually make this entire plot here. Especially galaxy archaeology, where we're going to measure the Milky Way dwarfs, the M31 halo, we're going to measure stellar streams. So I think PFS has a lot of potential to probe these models. And just last thing I'll talk about, it is that if this is an axion, this also interacts with photons. So you can also have all these other experiments to also try to probe the mass of this thing. So I think the future for axions and ultralight dark matter is very interesting. Like I said, I won't have time to talk about the superfluid dark matter, but please, if you have any questions, I will be very happy to answer in the question section. And with that, I'll conclude. I'll leave my conclusions here. And thank you very much.
Thank you very much, Elisa, for this excellent talk. For the people following the talk on YouTube, thank you for joining us. If you have any questions, please post them in the channel, and Elisa will try to answer them later. And we'll be back next week with a seminar on dwarf galaxies and their dark matter content from a cosmological simulation perspective. Goodbye. Now breakout rooms.